Okay, so last class we learned how to inject shellcode to the stack. We actually use multiple ways to do that. We put in environment variable, command line arguments, and also if there is a buffer overflow directly, we can put the shellcode there. But all of those three approaches, the shellcode eventually goes to the stack. Right? So today we're going to learn something new. First, we will learn what if we cannot overwrite the return address. So far, we have been overwriting the return address. So return address is a function pointer, it's a code pointer. We overwrite that. Eventually, we go to wherever we want to go. What if we do not have the ability to do that? We're going to use the same shellcode as before. So the attack we are going to do today is called string pointer attack. The name doesn't really matter. So what we do is we try to overwrite the saved EBP or RBP on the stack. Remember that we have saved the EBP, RBP, then at a higher 4 bytes or 8 bytes, we have a return address. So if we want to overwrite the return address, so far, we need to first overwrite the saved EBP, RBP. And right now, all those exploits, we're putting garbages there. We don't really care about their value. So in this class, we are going to only overwrite that instead of overwriting the return address. So this is overflow 6. So I didn't call it overflow return because we're not directly overwriting the return address on stack. Very similar to previous examples we have seen. The only difference here is the buffer is small, but that's not really important. What important is the bug here. There is a memory copy here. This buffer, you print out where the buffer is. Then there is a memory copy, and the memory copy will copy 12 bytes from the command line arguments. Okay, only 12 bytes. And in this address space, there is no function of print flag, no function of print files, which means I want you to inject shellcode there. At this point, I want you to inject shellcode. Second half of the class, even we will learn some new approach that you do not need to inject any shellcode. So this is what the binary code looks like. First of all, we try to figure out where the buffer is, right? So there is a memory copy. The memory copy takes 3 arguments. The first one is destination and the source, then 12 bytes to put there. So we should say 3 different pushes. The first push the address of the buffer. The second pushes the address of the source, which is the command line arguments. The third push should push just 12, right? So we say the function call here, memory copy. Before that, we say this is actually the last push, which is the first parameter in this case, which is the buffer. And buffer is at EBP minus 8, right? So we know buffer is 8 bytes. The beginning of buffer to the saved EBP is 8 bytes. Then we have push EBP plus 8, okay? EBP plus 8, that's basically where P is. That command line arguments. Then we find the push C in hex, which is 12. Okay, so that's what matters. Then now we have the ability to overwrite from buffer, from the beginning of buffer to 12 bytes, okay, which means we can overwrite buffer, we can overwrite saved EBP, but we do not have the ability to overwrite return in this case. Let's assume we are overwriting the saved EBP to the value 4a's. Then what will happen after we return? So here, we have a return instruction at the end of lawful. So what will happen after this? Push.
Basically we pop out the return address into EAP and the next instruction starts
Okay.
executing. And then from there, the saved EBP will be pushed onto the stack again.
Not necessarily. The first half is correct. Okay, the first half you said the return address here will be popped into EIP, the PC. So what is this address here right now? This is save the return address. What is it?
Address after the call.
Which function it is in?
Main.
In the main function, right? So because we didn't override this part, so actually it's an address in the main function. So after we return, where are we returning to? We're returning to the instruction.
Below the file.
Exactly. Okay. So we're not returning to push EBP, right? When you say we return to push EBP, you mean we're returning to a new function,
Okay.
but here we're not doing that, right? So let's say we actually return to the next instruction after call, which is an add in this case. Okay. We're not returning to the beginning of this or any other function. Okay. Then eventually the main function keeps executing. So far, there's no errors because here we're not really using the EBP to dereference anything anyway. So no errors, but eventually the main function will also return. Okay, which return to that, we say start main, whatever. Then the main functions are at the epilogue, there are two instructions, leave and return. Leave is equivalent to move EBP to ESP, then pop EBP, right? So let's say what will happen. Previously, we put 4A's here, and ESP points to. So let's say here, we first move EBP to ESP, and EBP, because it's already popped from Waffle. So EBP will have the value of 4A's, right? Then this place, we're moving EBP to ESP, copying the value of EBP to ESP. So both of them will have the value of 4A's. Then the next instruction, we're going to pop EBP. So what is pop EBP? We're going to pop whatever ESP points to minus. Put that
Into
no,
ESP.
into EBP. So in this case, we don't really know what ESP points to, right? ESP, I mean, we don't know the value, but the address is 4A's. So we are going to dereference that address. And most likely, that's not a valid address. So at this step, we get a segmentation fault. Okay. Then after that, ESP will increment 4 bytes. So it becomes AAAE, something like that. So this is why if we just override EBP with some garbage value, we're going to get a segmentation fault. Overflow 6. This one takes input from command line argument. So let's say, how big is buffer? 8 bytes. 1, 2, 3, 4. I just put ace. So eventually you get a segmentation fault here. Yeah. So when you say a segmentation fault, it means you find, most likely you find a memory bug, memory safety bug. And we want to turn that memory safety bug into an attack. We don't want to say a segmentation fault. We want to fully control the victim computer in this case. Then how do we do that? So the idea of this actually is very simple. What is saved EBP? What does it point to?
An address of memory.
Yes, it points to the address of the memory. In that, at that address, what is the data structure? What is the meaning of that? What's the semantics there?
It's something that will exit.
Okay. That's correct. So basically, it is the stack frame of the previous function. In this case, previous function is the main function. And the main function's stack frame, every function stack frame has a similar structure. There is a saved EBP, which points to the previous function's stack frame. Then there is a return address. Then there are parameters, right? Similar. Okay. So in this case, we cannot overwrite the return address of Wolf's stack frame directly. We cannot directly overwrite the return address of the main function's stack frame directly because it's even higher. We cannot directly overwrite that. But we can overwrite where is the main function's stack frame. Okay? Then what we can do, we can create a fake stack frame. We can create a fake stack frame for the main function, not for the volatile, okay? For the main function, then on that stack frame, we will have another saved EBP, which we don't care, and have a return address. So when main function returns, it will return to wherever we want it to return to. Make sense? Okay. Let's say we have a value X in this place. Let's say we have a buffer. The buffer's address is X. In this case, I actually print out where the buffer is for you. Okay. Then, if we just put EBP, the saved EBP as X, this is what we can overwrite. So what will happen?
Well, saved EBP's location is now the bottom of the buffer.
Yeah, exactly. So when the function Wolfu returns, the main function will have a new stack frame, and that stack frame's address will be the buffer, okay? That's where you can overwrite. Okay, then for this part, what is the data structure here?
That's a stack, it's like part of the stack frame that you return to it. So up above, it's gonna have the return address, what it thinks is the return address.
Yeah, where is the return address? This 4 bytes or this 4 bytes? Yeah, the upper 4 bytes is a return address, right? So this lower 4 bytes, the value doesn't really matter. Okay, so the upper 4 bytes, if you put the share code's address there, then the lower 4 bytes, you don't need to do anything, basically. So that's one way, then eventually return to our share code. That's the first way we can do this. There are many other ways. Let's say we can. It doesn't have to, this value here doesn't has to be X. It can be also other things. Let's say you put the share code's address in an environment variable. Then you just point to an environment variable, right? That also works. And also you can point to actually 4 bytes higher than lower than this. This address is X. What we put here is X minus 4. So main function, the frame stack will be somewhere here, right? X minus 4. Okay. So then to main function, this 4 bytes is saved EBP. The value doesn't matter for us. So even if we cannot override this, doesn't matter. But we can override the next 4 bytes. Then we put the address of the share code in the next 4 bytes. The upper 4 bytes doesn't really matter, right? So those are 3 different ways we can exploit this. Okay, so let's try this one by one. Let's just use this share code right either. The one we directly get the flag. Huh? Don't see any worse. Yes, oh, there's one.
One to the right.
Yeah, let's see this one. That's it. So that's our share code. We can only overwrite for 8 bytes. Let's do the first approach. First approach is we want to, this program actually tells us where the buffer is. Let's write it. It doesn't? Oh, it does tell us where the buffer is in this case. So it tells us where the buffer is. Then we want to put, we want to save the EBP to point to the buffer, right? This takes input from command line argument. So the buffer has the fake stack frame, which means the first 4 bytes don't really matter, right? Then the next 4 bytes, I'm writing this way to make it clear, the 4 bytes. The next 4 bytes should be the address of our share code, right? So our share code is at AD, can do a say 8. Add in there, PA, FF. Then, there's another thing, is when the address may change. Say, now we see the address is, the buffer's address is here. But when we run this, the command line argument is only 6 bytes. We run this again, the command line arguments will be 18 bytes. So the buffer will change a little bit, but we can adjust that later. Let's say if the address is 44 B2 FF. Okay. Oh, didn't change this time. Okay, so well, the C library did some alignment, so it's not really changing. So in this case, this part is we're overwriting main function, no, valfools save the EBP, and now it points to our buffer, and our buffer has those addresses. One is the main functions save the EBP, value doesn't matter, then it's the share code's address. So this address here is critical. It has to be correct, right? So if we change 1 byte, it's not going to work, right? Okay, so what if we change this to 0? So the fake stack frame will be 4 bytes lower, which means these 4 bytes now becomes the return address. And the higher 4 bytes value doesn't really matter. So whatever 4 bytes here, then remove this part. It will also give us a flag, right? So obviously every byte has to be correct. If you change 1 byte here, it's not going to work. If you change 1 byte here, it will work because we have a huge knob slit there. So what if we do not know this address? Here, the program actually print out buffer's address to you. What if we do not know that address? Then it's a similar problem as what you solved in return 7, actually, right? What we do is we can put a share code, we can put the address to environment variable. So let's create an environment variable. In the environment variable right now, we already have share code, right? Now what are we trying to create here? What? No, we're trying to create the fake stack frame, right? So what does a fake stack frame look like? Basically two things. One is save the EBP, one is return address. And save the EBP's value doesn't matter. So what only matters is the return address. So our stack, let's call it fake frame like this, FF. What should we put here? Which address? Yes. So we're putting this into environment variable, right? What we only cares about is a return address, right? So we only need the return address. But another issue here is when we're not know the exact location of this. So what do we do? We make many copies of this return address. Make sense? Let's say we have 500 copies of the return address. We're going to use one of them. We don't really care which one. Right. So the return address here is the one we used before. Let's say it may change. 500 times of this. Then let me check the S code address again if it works. Now it changed. Now it's D2 D9. So FF D2 D2 D9. So EE should be fine. Okay. Check again. Good. Our fake frame's address is D77C. Okay. Then in this case, what our exploit look like? Our exploit, first we have, are we still using the buffer, that 8 bytes? Previously, we used that 8 bytes buffer to store this 8 bytes, to store the address of the fake stack frame. Now we're not really using this anymore, right? So 8 bytes of garbage, what important is here? We directly put that. So here we can have 8 bytes of garbage. This part doesn't matter. Then we should have the address of FF somewhere. So we have D77C. We can add something there. So let's say we add 80. D7. This may work, this may not work. Okay. It doesn't work. Why it's not working?
Is it about alignment? Like we're getting halfway through the return request?
Exactly. It's about alignment. So we only need to change maybe 2 bytes, right? But we don't know. We have to try here. So let's try 81. Doesn't work. 82. Doesn't work. 83 works. So it's about alignment, right? 83. So now we know 83 works. What other address will work?
87.
Exactly. 87 would work. 87 should work, right? 7, then 8B should work, right? But if you have 1 byte off, it's not going to work. Okay. Make sense? Yeah. So this is how we combine multiple techniques together. We inject the shellcode onto the stack. we do not directly overwrite the return address. We overwrite frame pointers address. So we create many fake stack frames in other addresses and point to that. So that's the basic idea of this attack. Let's try to summarize. How do we, yeah, go ahead.
If we somewhere assume that at which point did we jump to the shellcode? Was it in Valfo or
No.
was it from main?
Main.
Yeah, if it was from main, did we assume that main hasn't used its own stack variables at any point of time? So it didn't create any local variables.
Yes. So in our, that's a very good question. So you can say that the main function here is very simple. Main function calls Valfo. When Valfo returns main function doesn't do anything else. If main function does many other complicated stuff after the Valfo, they may trigger segmentation fault before you can return. Yes, yeah, that's right. Okay, so the conditions we need to pull off this attacks. First, the ability to put share code onto stack. The stack should be executable. We should have the ability to overwrite the return address on stack before a return instruction is executed, or we overwrite the saved EBP. And we need to know the address of the share code. We need to know where we are returning to, right? Those are the conditions we need. So next, we are going to study the defensive solutions people, the research community, and also the developers community came up with in the last 25 years. Yeah.
Can you tell those things?
Yeah. In the last 20 and 25 years, and why they work and why they do not work, and how to bypass that. So all security solutions or defensive solutions, we can divide them into a direct solution or indirect solution. When we say a direct solution, we talk about a solution that can eradicate the problem, really tackle the core of the problem, address the problem. Okay, when you hear words like that, you think that's a very good approach, right? Not necessarily, because usually they are very expensive, computationally expensive. They could be very slow. They are good in theory, but they are impractical in the real world. Most of the solutions we are using today, they're not perfect. They have all kinds of issues, but they are adopted on all of your laptops, phones. Then there are indirect defenses that in theory, they have all kinds of hopes. There are problems here, there. However, they are very fast. They are very simple, but very fast, and they are widely deployed. Some examples. One approach is called base and bound check. That prevents all kinds of buffer overflow. That's a direct defense. Then we were studying what is stack canary or stack cookie. That's an indirect defense deployed on all your devices. Has been there for 20 years. First introduced like maybe, I think 20 or 22 years ago, or maybe a little bit earlier than that. Later you will see how simple it is. Then there is the data execution prevention, which you saw in return 7. Okay, basically means the stack region or some other memory regions should not be executable. Even if you inject code there, it will not be treated as code. So the base and bound check approach, in theory, it's it's perfect. For any pointers in a program, let's say there is a pointer. There is a pointer A in the program. For any pointer in the program, the compiler may try to instrument two more pointers for that pointer. One pointer is called base, another pointer is called bound. Let's say if you use dynamic memory allocation, you malloc some memory, you do a malloc 512 bytes and assign that buffer to the pointer A. The compiler will instrument code, or may not necessarily be compiler, it could be all runtime as well. It will say, for the pointer A, it associated two another pointers. One is the base, another one is the bound. And the base is just where the beginning of the buffer is, wherever the libc allocate for you, and the bound is the end of that. So for the pointer A, no matter what kind of operations you do, we are going to check if you are dereferencing or either read or write or do anything else to a memory location that is out of that range. Okay. For example, you can do A0, that's legal. You can do A511, that's also legal. However, if you do A-1, it will not be illegal. Or do A1000, that will not be illegal, will not be legal. However, the C language itself allows you to do that, right? The C language itself doesn't check that. So we have a lot of layer on top of the C language to do this. However, this approach is very, very expensive. Right? First of all, for any pointer you have in this programming language, you need two more pointers, at least two more. For any propagation, if you assign A to another pointer, this kind of properties also need to propagate to others. It can get very complicated sometimes, like this case. Even the semantics could be quite complicated. So in theory, they are good, but they will be very slow, and even correctly implementing this sometimes could be challenging. In short, storage, maybe 2 times overhead on storage. That's only for storage, but for assignment, one operation, previously it's one operation, now you need to do multiple operations, at least 2 more. Or for any dereferencing, you need to add 2 comparisons there as well, right? So you can imagine the program will be much, much slower using this approach. This approach was first proposed in a top programming language paper published in PRDI in 2009. I think they also have, they actually, at the same year, they use some hardware features to make this slightly faster, published in a top architecture conference as well. But even that is not very practical, still very slow. So next we are going to talk about some more practical approaches that really adopted in real world. The first one is called data execution prevention. This is a feature you just saw. On different architectures, they have different names. Some architecture call it DEP, some architecture just call it not NX, not executable. Some architecture call it write or execute. Means if a memory region is writable, it should not be executable. Okay? Writable means users can change that, attackers can change that. If users, attackers can change that, we will not make it executable. But this is counterintuitive because we have self-changing code. We have just-in-time compilation. So any of you heard of that? Yeah. Which require you to modify the code, right? So that's why this feature right now is we mainly use it for stack because there's no reason the stack should be executable. There's no reason you should put code onto the stack. Right? So this approach basically takes out of this condition. The stack is executable, but making the stack not executable. Okay. A little bit of history of this. In your computer organization class, you probably learned that there are two different ideas for designing your memory or any kinds of storage systems. One is called the Harvard architecture, which stores the machine instructions and data in different memory regions. And this is a high-level idea. This can be implemented at all kinds of layers. It can be implemented at a hardware layer. Let's say we have separate memory regions, memories, okay? Some of the memory could be flash, could be DRAM, could be SRAM, whatever. Some of memory regions will only store instructions or code. Some other regions will only store data. Then even the CPU can have different circuit. The CPU will only fetch code from the memory region that stores code. Okay. It will never fetch code from the memory region that stores data. Okay. You can separate them at a hardware layer. You can also separate them at a software layer. The hardware support everything, right? So the architecture we usually use is the von Neumann architecture that we store data and code together. Okay. For the memory we're using, the DRAM, for all computers, the DRAM, it can store code, it can also store data. We don't really separate it. Right? At least at the circuit level, we do not support that, separate it. Then because of the buffer overflow we just learned, because of the shared code injection approach we just learned, 20 years ago, the CPU vendors like Intel and AMD, they started introducing a new hardware feature mainly on the MMU part, the memory management unit. In MMU, you can specify this memory region as read, write, and also executable. Three permissions. Previously, before that, only two permissions, read and write. Read implies executable. Okay, how they separate it? There's read, write, and executable. Okay. So AMD introduced this non-executable bit 20 years ago, 23 years ago. Then Windows and Linux, they started adopting this hardware feature 1 year later. Basically, they need to change their implementation of the memory management code, right? To leverage this hardware feature. GCC also has a parameter option for this. It's this -z executable stack. By default, we do not use this option. When we do not use this option, it means the stack is not executable. Okay. So for the programs you have been hacking so far, most of them, I use this option to make the stack executable. So by default, it's not executable anymore. So when you compile this in GCC or other compilers, LLVM is another compiler we usually use, especially for our research. We use more LLVM than GCC because developing LLVM classes is much easier than developing GCC modules. When we use that option, the GCC or LLVM, the compiler, will basically mark the resulting L file as the stack as executable. As you can see, this is OF6. If we do a read elf, we can say this region, this is a stack, is executable. Okay. So otherwise, by default, it will not be executable. But they only mark the L file. Eventually, it is the loader and operating system. They need to honor that setting. Okay, they need to respect that. So every year we participate in a capture the flag competition called the Embedded System, CTF, organized by MITRE. So actually this semester we are doing that. We have a team. So next year you guys can participate. So what we learned, we found from last or several years of competition is, first of all, that competition is about developing an embedded system, a secure embedded system, and give that system to other teams to hack, right? So you're not developing a system on Linux, on Windows. It's in a microcontroller architecture. We analyzed every team's design for the last 2 years. We realized that many teams, when they compile their systems, they make sure the stack is not executable, okay? They want to make the system more secure by changing the GCC options, okay? So after that, the GCC will generate an L file. The L file will say the stack should not be executable, okay? However, you're not running this L file on Linux system. If you run this on Linux system will check the header and say the stack is not executable. So in the kernel, it will change the MMU settings to make sure the stack is not executable. Okay. We're running this on an embedded system. There is no OS. So there is no code in that embedded system to honor the header bits of that L file. And we find out many teams are doing this. So then we conduct 17, 15 interviews. We ask them, do you know that your security setting is not really working, right? Most of them didn't know that. So that's some interesting finding. So what DEP cannot prevent? This cannot prevent corruption of the stack or function pointers or other critical data on the heap, first of all, because and also as long as the return address, if you override the return address points to some legit code section, not data section, it's still executable, right? So how do we bypass this? The first approach is the return to deep-C attack, especially for the 32-bit version. This was discovered before this hardware feature was introduced. Okay. This is discovered by the hacker. His pseudo name is Sonar Designer. If you search this, you can actually find his true identity. I think he made several major contributions, not only discovered return to deep-C attack. You actually already learned how to use this approach. We talked about how to do this kind of attack last week. I just didn't tell you this is return to deep-C. This is basically return to a function already in the address space, and it can take different parameters. Yeah. It's just, you can return to a C library function. You can also return to a function that is in this executable. In the print file example, return 7 example, you're not return to the C library function, you're return to another function in the executable, but it's the same thing, right? So the previous approach was like this. In C library function, there is a function called system, okay? The system function will create a new process. So you can imagine, under the hood, it will call a system called execve there. And the parameter here is just the path of the new process you want to create. The problem is in modern systems, when you do this, you will not have the root privilege. It's the same problem as we had in our first shell code. You do an execve of a new shell, you can get a shell, but it's not a privileged shell. So let's say this is basically our another example. It's still overflow return 4, but now I changed it a little bit. This one, the stack is not executable, but you can use the approach we just learned. you can overwrite the saved EBP. Oh no, this one you cannot even do save the EBP because the save the EBP one, we inject the shellcode there. The shellcode is not executable. So let's say, we can actually do this, do a return to system. Let's do this, but it will not be a privileged shell for us to capture the flag. Overflow. Overflow return for. Overflow return for. Too many versions of this. No, yeah, it should be this one. No executable stack. So the stack is not executable. So if we run this program, let's say we have this. So the first thing we want to do is we want to find out where is the address of the C library function system, right? How do we do that? Can we do an NM on this program to get that? Can we? So we do an NM on this one. Do we get a system there? We don't, right? Why we do not get the system there? Means the system function is not really there, right? Why it's not there?
In deep C.
Yes, because it's not really in this executable. It's in the C library. Okay, so only when you execute the program, the OS will load the library there. So one way to do this is on our system we can just debug this. We run. We set a breakpoint. Main. We just run this program. Then we can use just the P command. P means print. We just print the address of the system function. So P system. So system right now there it's a symbol. We want to print out the symbol. Then we can say this is the address. Okay, that's a C library address. Obviously, it's not on stack. Stack will be FFFF, right? It's a much lower address. Okay. Then let's say how big our buffer is. Our Overflow main function. So Overflow, this is 30, which is 48. 48. We want to overwrite the return address. This one takes input from. This one takes input from STD input. So should look like. 48 bytes of garbage, then another 4 bytes for the save the EBP, so 52 bytes. Then we have the return address. Return address should be the system's address. So it's 80 F7 E0 F7. So that's the address of the function system. Then after that, we need to give it a string, right? After that, we need 4 bytes of garbage again.
You're not seeing F at the
What?
end of the address.
F7, yeah. Then we have the address of the string. We can put that in environment variable, like what we did for the flag thing. But the string here should not be the flag, should be bin sh, yeah. Okay, we need that. Okay. So we need to export AA. Want to have maybe a lot of slashes, 500. Then after that, bin sh. That should be good. Okay, that looks good. Then we'll get an address of that somewhere here. Okay. Now we have that 5 bytes. So we'll have three DD FF.
It's 20, or
What?
the address is 20, are you?
Yeah, I'm trying to add something because we have a lot of slash. So the 20 here supposed to point to AA. It will not be that slash anyway. So I'm intentionally adding many bytes there. We can add many more actually. So
And why do you have the 4 case?
why do I have this for? This is the same as the return 7. The challenge in last homework.
Okay.
Yeah. For this.
That's
This is a
that's
return
the
address.
return address of the next function.
Yes. This is a return address. Then this is a parameter for that function. Yeah, so last class we spent a lot of time explaining why we need this 4 bytes. So if you don't remember that, go back to the videos. Let's say after this, we need a cat here because we want to type something after this. After this, we type into this. Hopefully it works. See. Yeah, it works. See? We do get a shell, but it's just a CTF shell. Yeah. Because we didn't, there is an exe-CVE, and before that exe-CVE, we do not have the chance to do that set SEUID again. Okay, so return to libc. So far, the attacks we learned, they can be classified as control flow hijacking attack. Control flow is defined as where the order in which the statements should be executed. Statements is a very high level term here. At the machine level, basically that's just instructions. If you look at this at a quite a high level, like a control flow level or function call level, the statement you can say that's just a call to different functions. So if we violate the predefined control flow, then we're doing this control flow hijacking attack. You write a program, even though that program has a function called valfoo. If nothing happens, no attacks, valfoo should always return to the main function, right? That is a predefined control flow. Okay. But now we are overwriting the return address, so we are hijacking the control flow. Afterward, to hijack the control flow, we need to change a code pointer. So far, the code pointer we're using is a return address. There are other code pointers you will see in the homework, not today, maybe next week, like a function pointer. function pointer is a code pointer. A function pointer could be a variable. It could be a global variable, it could be a local variable, it could be overwritten. Also, we talked about lazy binding before, remember? When we call the printf function twice, it behaved differently. The first time, it go to a stop to actually resolve the address of printf. The second time, it calls printf directly. So, which means there is a table to store the address for printf. So that table is full of function pointers. If you can override that, you can also hijack the program. That's something we're going to do after the midterm. There is a subcategory of control flow hijacking attack. We call the code injection attack. Is what we did last week by injecting shellcode. We inject the shellcode there. Eventually, we want to hijack the control flow to execute our shellcode, right? That's the purpose of injecting the shellcode. So that's why it's a subclass of the control flow hijacking attack. Then we have code reuse attack. We already did several examples of code reuse attack. So this return to libc attack we just did, it's a code reuse attack. We didn't inject any code into our address space. The one you did in the print flag return 7 is also a code reuse attack. You are reusing existing functions in this case. After midterm, we're going to learn some advanced techniques. We're not going to reuse a full function. So far, you have been reusing full functions. So system function, the return, the print flag function, print file function, right? We're going to leverage some gadgets in the address space. Gadgets, they are just sequences of instructions. We'll talk about that later. Okay, so this one we can also revisit later. Let's look at the second defense. The second defense, which is still a popular research topic right now, it's called the shadow stack. Actually, in my lab right now, we have an ongoing project developing a new type of shadow stack for embedded systems. The idea of shadow stack is also very simple, and a lot of compilers right now already support this. I don't remember if GCC supports this, but the LLVM definitely supports this. So you see, the problem we are facing in previous attacks is the return address is somehow overwritten by the attacker, right? So what if we take out that ability of the attacker? So what if the attacker doesn't have the ability to overwrite our return address on stack? Right? So how do we do that? We maintain two copies of return addresses. So the attacker, for the previous examples, is string copy, memory copy. They can only overwrite the original stack. But we keep another copy of return address somewhere else, which is harder to overwrite. Then there are two main ideas of this. One is called the traditional shadow stack approach. Another one is called the parallel shadow stack approach. A similar idea. Let's say this is our main stack. So stack goes down. So we have parameters for, let's say, function 1. Then we have a return address. We have the EBP, saved EBP. Then we have the next function, similar data structure. The third function, similar data structure. Then the fourth function. Then we have another shadow stack at a different place. We just store all of those return addresses here. Okay. very simple. Another approach is we also store them at a different address. However, they have a constant offset to the original address. The benefit of that is later you will see the code will be shorter, so the execution will be a little bit faster. So if we look at the code, everything will be much more clear, let's say. So here we have the implementation of the traditional shadow stack. And this is at the beginning of the program. So this is, this slide is all about traditional shadow stack. And the upper one figure is for the prologue. The lower one is for the epilogue. So we can say at the beginning of the function, what we are doing so right now is we push EBP, right? We move EBP, move ESP to, no, move EBP to ESP. Yeah, move EBP to ESP. Yeah, then we subtract something. So in addition to that, we are going to do something like this. This is AT&T syntax. The GS here is another system register. So basically what we're doing here is we're storing the shadow stack at somewhere GS 108 offset, basically. So that will be our shadow stack pointer. Our stack pointer is a physical register, SP, okay? Now we don't have another physical register to do this. So we just use a memory variable, a memory, 4 bytes of memory as our shadow stack pointer. So here in the paper, they call it SSP, the shadow stack pointer. The shadow stack pointer is at GS plus 108. That's a memory location, okay? We first subtract 4. So we're moving our shadow stack down 4 bytes. Then we're copying, so this is the AT&T syntax. So the second argument is the destination. So we're moving this one to EAX. So we're moving the shadow stack's address to EAX, the register EAX. Then where's the return address? Because this is instrumentation after that, it could be at the beginning of the function. The real return address is already pushed onto the stack, okay? So the real return address is pointed by the register ESP. So this instruction is moving ESP, what ESP points to, which is our return address, to the register ECX. Then we're moving the return address from ECX to where EAX points to, and EAX points to our shadow stack. Okay, so we didn't change the original stack. The return address is still there, but we made another copy by using those 4 instructions to another place. That's it. That's the beginning of the program. So when we returns, before we return, what we can do is we first the shadow stacks pointer move to ECX. Then add that we dereference what ECX points to. Okay. Move that to a register EDX, then move EDX to where ESP points to. So what are we trying to do here? We are overwriting the original return address from the shadow stack, right? So the assumption here is the original stack may be overwritten, but the shadow stack is not. So we do not care what the original stack has. We just take the copy from the shadow stack. Okay, make sense? We copy that back to the original stack. Then we return. Okay. So see, this will add 9 more instructions to one function. If that function wants to be protected, 9 more instructions. And a lot of memory operations there, so it's will be a little bit slow.
Why do we move to EDX there? Why can't we directly move from ECX to ESP?
From ECX to where?
ESP.
There's no instruction of that. You're not moving to ECX to ESP. You're moving to where the memory ECX points to the memory of ESP points to.
But why do we have EDX?
That's
as
just
an
a
intermediate?
temp register. You can use another register. Because you don't have an instruction to move directly from this memory to another memory address. So at least the 32-bit, there's no instruction like that. Yeah. There's another way to do this. In this way, we're not directly copying from the shadow stack to the traditional stack. Instead, we're going to compare whether the shadow stack and whether the shadow stack and the traditional stack, the original stack has the same value, right? So we get the shadow stack pointer to ECX, we dereference ECX, move that to EDX, then we compare EDX with where ESP points to. Okay? ESP points to the original stack. If they are not the same, then we just abort the program. Okay. So that's the traditional shadow stack. So the benefit of traditional shadow stack is you're not going to use a lot of memory, right? Because you are not wasting space here. Another approach is the parallel shadow stack, where the original return address always have a constant offset, a distance to the return address on the shadow stack. The benefit of this is the implementation is much more simpler. You can see we are only using 4 instructions to do this. Okay. So this is a prologue. We are going to pop RSP where our ESP points to this constant offset. Okay. So this pop instruction will actually move data from memory to memory. The move instruction, there's no move instruction to do that, but the pop instruction can do that. Okay. So by doing this pop, because popping is not really clearing the original stack, but it will move the ESP 4 bytes higher, right? So by doing this popping, we're actually copying the return address to the shadow stack. But the side effect here is ESP will move up 4 bytes. That's why after that, we subtract 4 bytes from ESP. Okay. So only 2 instructions, we're making a copy of the shadow stack. The epilogue is almost the same. Yeah, just do a push. And then, so that's why the parallel shadow stack is faster, at least on this architecture. The paper, so this is from the paper published in 2015, almost 10 years ago. The paper says that the runtime overhead for traditional shadow stack is kind of like 10%. Okay. So 10% is a lot. The parallel shadow stack, they tested the overhead is like 3.5%. So that's the second approach, shadow stack. It is not widely adopted in real world, but there has been some pushes try to adopt this. Like I said, LLVM has good implementation of this. GCC, I'm not sure. Yeah. The third approach, stack cookie. This one, yeah, go ahead.
If the attacker can see that there is a pop operation happening.
Yes.
That's a fixed offset.
Yes.
What prevents him from just, or them from going to that new address?
So the assumption here is the attacker cannot overwrite the shadow stack, right? So how do we really achieve that? There are many different approaches. And that part could be very slow. So in our ongoing project, we are using a hardware feature to make that small memory region not writable, basically. After that epilogue, that memory region will be changed to not writable. No one can write to that. Okay. There are some other approaches, not necessarily smart. For example, there is approach I say is that memory, that shadow stack will be in the kernel. Then it's safer. So assume the attackers can write the user and memory space, but cannot write the kernel. But that's obviously very, very slow because then every function needs to do a system call into the kernel, will be very slow, yeah. That's also why shadow stack is not necessarily a very good approach, yeah, because you need to protect the shadow stack itself. So the third approach we're talking about today is stack cookie. So this is widely adopted everywhere. But also for embedded system, no other devices, this approach is not really working. This is specific to sequential stack overflow, like those memory copy, string copy, where you sequentially overwrite things. It can defeat that. This was published 26 years ago, back in 1998, published in one of our best security conferences, Usenik Security. The original paper name is Stack Guard, and they implemented this on GCC, yeah, 26 years ago. This approach actually received Test of Time Paper Award maybe 15 years later, after this paper was published, because this is so practical. It was widely adopted everywhere. This is a compiler-based technique. A lot of techniques we talk about are compiler-based, which means the developers, they don't need to do anything. They do not need to change their source code. The compiler will automatically add some code there. Add code, that step is called instrumentation. The compiler will instrument some instructions there. It's transparent to the developer. So this is a compiler technique to try to eliminate buffer overflow vulnerability. Obviously, it's an indirect approach, so it cannot really eradicate the problem. No source code changes. It just patches the prologue and epilogue of the function at the compiler level. So this is our original return 4, overflow return 4. The buffer, 48 bytes. And we already look at this piece of code. Okay, so this is a piece of code we attacked last week. This is a version that there is no stack guard or stack cookie or stack canary, whatever. And this is a version you overwrite the return address on stack. Okay. Source code level, they are the same. Binary code level, they are different. This is a version you attacked last week. So if you add this stack cookie protection, the code will look like this. Okay. Exactly the same C source code, 2 different versions of binary code. The main difference is in those 2 red boxes. Okay. So let's take a look. What are those? In the first red box, it first moves some value from GS. GS is a general register. It's not a general register. It's called a segment register. It's one of the very old registers, but now we repurpose it for something else. So anyway, we're moving from memory location. This memory location is at GS14. Just remember that. From that memory location, we're moving 4 bytes to register ECX, okay? We don't really know what are the 4 bytes. Those 4 bytes are the canary values. It's a random value. Most of 3 bytes of that are actual random value. On Linux, the last byte is always there. So those are random values retrieved from the kernel. Kernel will generate a random value whenever the program is created. Those 4 bytes will be placed at that location, GS14. Okay. Then At the beginning of this function, that 4 bytes is moved to register ECX. Okay. Then ECX is moved to where? EBP minus C. Okay. That 4 bytes, random 4 bytes, is moved to the stack, and also at an address lower than the saved EBP. So we have return address on top, we have saved EBP, then somewhere EBP minus C, C is 12, right? Then we have this random 4 bytes. Okay, that's it. Then after that, we have our buffer. So previously our buffer is at EBP minus 30 in hex. Now our buffer is at EBP 34 in hex. Okay. So the buffer may overrun. Okay. So when you try to overwrite this return address, you need to first overwrite the buffer, right? Previously, you first overwrite the buffer, then you overwrite the saved EBP, then you overwrite the return address. Now there is something in between. There is a random number in between. When you overwrite the return address, you need to overwrite the buffer, overwrite that random number, overwrite the saved EBP, then overwrite the return. Okay. So the assumption here is you don't know what that random number is. So when you overwrite the random number, previously we were just using some garbage values there, right? Then when the function returns, we're going to check if that random number has changed. If that random number has changed, we think maybe the return address and everything else has also been modified. So that's with the sequence, this stops the sequential overwrite. If you have a pointer that do not do a sequential overwrite, can directly override the return address, this approach will not stop you, right? Okay, so in format string, we will say we have a much more powerful tool. We can overwrite any address. We don't need to do a sequential overwrite. So the string copy, memory copy, you need to do a sequential overwrite. So in the second red box, this is before return. We're going to check if that random value has been changed. We first move that random value, which from the stack, which is EBP minus C, to the register ECX, right? Then we compare ECX with our original stack Canary value. Of course, we assume this value cannot be changed. If they do not match, then we will call this function the library function __ stack check fail local. Basically, it print out something like stack smashing detected, something like that. So if we run this version, the same C code, just a different version of compiler. Run this program, take the input from where? This one. Remember this is command line, or let's just try command line. Oh, it's std. Nice. How much byte we need? Previously it was 48 bytes, but now we are at, where's the buffer? 34. 34 and C. 34 is 52, right? C is 12. So that's basically 40 bytes. 40 bytes of buffer. So if we just do 40 bytes or 39 bytes, then this one we should not overwrite that random value on stack, right? So still IP the full, but 40 should be okay too. 41 we should. So this one we are overwriting that random canary, and eventually it calls that stack check fail function, which print out stack smashing detected, aborted. Okay, So this is why, this is how you stop this, okay? Very simple, right? Very, very simple idea. And has many problems. Should, can be easily bypassed. So we're going to talk about that soon. A little bit about that GS register. That's one of the oldest registers. Back in the 70s, they were there. So back in the 70s, the memory, we were not using paging, we're using segmentation. If you took the OS class, you may remember those concepts. Segmentation, paging. Now we're using paging. But before that, we're using segmentation, and those are segment registers. That's why it's called a CS, code segment. SS, what is SS? So DS is data segment. ES, I remember, is extra segment. I'm not sure about SS, FS, GS, what do they stand for? Yeah. But those registers are repurposed. So the idea here is very simple. The stack looked like this before. Buffer, save the EBP, return. Now we have buffer, we have 4 bytes of calorie, then we have saved the EBP. So if you can only sequentially override this, then you have to override the calorie. If you do not know the calorie value, the chance for you to magically just have the same value will be very low, right? So 64-bit version, almost the same, just that the calorie is 8 bytes. And they are at a different location, the FS28. Okay, but the idea is the same. A little bit about that GS and FS, where they point to. They actually point to something called thread local storage. It's not very important of those concepts. It's just a local storage for each thread. Okay. Some command you can get those address, but it's not very important. So the Canary values, what do we put there? One way to do that is just random numbers, random bytes. Also, there are some other ideas like put 0 there. Why do we put 0? Because some old dangerous functions like string copy, they stop at 0, right? So we put 0 there. Then there are some other terminators, like other functions may not necessarily only stop at 0, but also stop at other functions like new line or whatever, right? So that's why there are some other calories as well, but the most popular one is just a random number. Let's say, what we published a paper last year to talk about the calorie mechanism and why it's not working, especially for embedded systems. For Linux, for this one, we are working on. So for the previous example, every time you create a new process, every time you run that same program, like overflow return 4, every time you run that, it will get a new random value from the kernel and use that as a kernel, okay? But for embedded systems, how do you generate that new random value? The embedded systems, like a router, they may keep running there for 5 years without rebooting, and they may not have an OS. Everything is a bare metal system, is one big program, right? So they may have a calorie value, but that calorie value will never change, right? So here, every time you run it, you have a new calorie. But that is not also good enough. So that's why last year we wrote a paper talking about, the title is "The Calorie is Dead," or I think, or is the calorie dead? We're talking about this is not effective for embedded systems. We actually look at how Linux kernel generates this. So this is a start, the libc start main function, which calls your main function, right? This function will actually retrieve the calorie from here. So here, this one, those 2 lines. This function is actually retrieving a random number, And retrieving this random number eventually goes to the kernel to retrieve that number. And use that and put this in that GSFS address is this one, the thread local storage. Put it there. Then it will call the main function. The main function and other functions will start using that query back. So this was published, the paper was published in 1998. They changed the very old version of GCC. Then from there, many other companies, teams developed slightly different approaches. IBM developed something called the Pro Police. We're going to look at that soon. Then Google implemented new versions of this called Stack Protector Strong. This is a compiler option flag. If you want to protect all the functions, you need to give that option to the compiler. So some of those options will protect all the functions. Okay, some options were only protective functions with local variables, with buffers, because this will be very slow. That's basically the reason. It's a little bit slower. Yeah. Most Ubuntu packages are compiled with Stack Protector option. So there's a strong, there is a Stack Protector. Strong is the one protect every function. Yeah. Also, the Arch Linux compile everything with the strong flag option. So it will be a little bit more secure. However, also a little bit slower. So this is IBM's approach called Pro Police. Let's say this is a C code. The C code looks like this. We have local variables. We have A, B, C, D. A is an integer, 4 bytes. B is a address, is a pointer, also 4 bytes. C is a array of characters, a buffer, 10 bytes at least. D is 3 bytes. So the examples we have seen so far, we will know the order of those variables, right? The one appears first, we had a higher address on stack. So far, it followed that pattern. So we use the latest GCC to do this. So the native GCC will do that. The first appeared variable have a higher local address on stack. Okay. So the IBM approach is to randomize the address of those. Do not really follow their appearance in C code. They randomize that. Not only randomize, it could also put the dangerous ones to a higher address. Let's say C and D here is a buffer. They are more dangerous than the integer, right? Because when you overwrite, you usually overwrite a buffer, but you can also overwrite other variables. So they put them at a higher address. If they are at a higher address, means they do not have, if you have a sequential override, you don't have a chance to override the lower address. Okay. So they put a CD here, put an AB at lower address. So if you override a CD, you will not be able to override AB. That's basically it. Then they put a Canary there. So that's their approach. Okay. Just a little bit safer than the previous one. So next, let's see. Let's take a 5 minutes break. After we come back, we'll learn how to bypass this. Let's go.
What makes it safer to have C and D at higher addresses?
So in the previous attacks, we're doing a sequential override, right? You override C first, then we'll override everything above C, higher address at C. If you put C and D at a higher address, then A and B are lower address, then even if you can override C and D, you cannot override A and B because they are lower address. So in our very first example, which is before we have the override return, we have an override local variable. Remember, there was a local variable called authentication, auth, or whatever. Then you have a buffer. Then by overriding a buffer, you eventually override the auth. If you move auth down, then you will never have a chance to override auth, right?
Thanks.
We come back at 7:50.
No, no, no.
Like people actually have some like good things in this movie.
Maybe.
Like, I don't know.
I feel like I'm due for a rewatch. I was just thinking about, do you want to watch like a sitcom?
I have been watching this show that everyone recommended me so much. It has been really good. I thought it was all happy, good, fun vibes.
So no.
And then
Well, then.
favorite character passes away. And I spent all of last night crying.
Also.
It's actually not good, happy, fun
That's so
vibes.
fun. That's so fun.
Oh,
Yeah.
and like the tone shifts, like
Oh, no. That's not what I wanted. That's like not what I
the
wanted.
cute romantic scene, like fun, happy, like
Yeah.
upbeat. Yeah, I was like,
Jeez.
oh,
Yeah.
yeah,
Yeah.
it was a lot.
Yeah.
Oh,
Oh, man. Yeah, just don't have the capacity for it. Great.
I wasn't ready. And it was also like, last night was the first time I was watching it at home. So you think that I'd be watching like at the gym while I was like
Sure.
doing cardio or something like that, right? To just like not
Yeah.
crash out.
Right, on the treadmill.
I was like, I was watching on Netflix and it like auto played the next episode and I was so.
And you're like, Netflix actually didn't watch it. Wait a minute.
This is enough.
Wait, what show is this?
Well, here's the thing. I feel like if I tell you, I'm gonna ruin like the build up. I mean, like if you do watch it.
That's totally understandable.
So at one point, I'm gonna give you a rank of like 3 different shows that
Right,
I
I'm
start.
gonna, one of those things
Exactly,
might be it.
and one, like, they're all equally good.
Okay,
They all
great.
equally have good vibes,
Right.
except one of them,
One who's gonna have like a surprise,
like surprise terrible vibe.
horrible bombshell in the middle. Okay, cool. Well, right now I'm watching Arcane very slowly. So we're
I
in
couldn't get
mid-season
into
2.
Arcane.
I had a lot of fun actually. I did
Yeah?
too.
I tried to get into it, I'm a really big anime fan too, it just Didn't happen. I don't know.
Season one, just absolutely incredible. Then season two, I could not believe how bad it was.
Oh, really? I watched season one, didn't like it. I don't know.
Season two, just
The hurriedness of it.
Yeah.
I feel like you're trying to get.
like they had like 4 seasons of it, that they accidentally put into one season.
Yeah, when I got to
We're
like,
making
I
that.
got to like episode 4 and I was like, we've already had multiple time skips.
And
We are
multiple
moving and grooving.
different like random backwards character arcs where like Vi was a cop and then she wasn't, and then she was, and
Yeah.
then who the hell was like the homeless guy?
That's weird too, because I feel like they definitely have the fan base to do something like more drawn out.
Yeah, I
Yeah.
did feel like that is how the second season feels. 'Cause like it's all really good stuff that they're doing, but there's too much of it for one season, and so they're like crunching, but I don't know. I also had almost no expectations going in. Because I know
That's-
nothing about League of
It
Legends and I
was
didn't know
also
anything
like
about the show.
super hyped up for me.
Right,
So
I mean,
when
I was
watching
like,
it, I was like,
I was like, it was gay and it made people cry, and I was like, okay, that sounds like something I could get into.
although the
know.
last time someone gave me a rec like that, it didn't make me cry. I watched, have you seen Banana Fish?
No,
I watched people like it's gonna ruin you.
yeah,
They desensitized me to that. I was
Yeah.
expecting it, I was
Yeah.
going into it, I was like,
you gotta go in with no expectations.
Yeah.
That's ideally the way to
see,
go.
that's why I wouldn't do that to you. I already have like
Right.
3 other ones in
Right.
mind that do similar things in the beginning,
Yes,
so.
man, you're so ready, you're so ready.
Cause otherwise it's just like, I hate when people like ruin it in that way, you
Yeah,
know?
yeah, for sure, I feel you. But also the chances that I actually watch a show.
Oh, cause this one too, like, it's one of my friend's favorite animes, like ever. And he was hyping it up and I was like,
Well, that's the other thing, is like you have to set expectations, man.
yeah.
That's
So
always,
true. That's so
always.
true.
Yeah, everyone.
That's good because I feel like I was crazy when I was.
No, I have another friend, my one other friend who watched it, basically was like, the first season is great. Second one, they just tried to stick too much into it. I was like, I honestly hadn't thought about it anymore, and I think it's very true.
Yeah, it felt to me like. In season one, the characters were driving the story. In season two, the story was driving the characters. So it felt like everybody contributed to it. Whereas in season one, it felt like everyone was acting the way that they would act in certain situations. Imagine, because they're trying to make the right decisions.
Right.
And it's going on.
Right.
Season two, they're making just wrong decisions. They're just doing weird things.
See that, they're gonna say also, like, I'm watching it, I'm not watching it that day repeatedly, like, I'm paying attention to most of it, for sure. But even my.
He's not doing that.
He's
He has
not
everything.
Then we should have had the break earlier. Okay, so next we talk about how do we bypass this Canary mechanism. So let's see. There are many ways we can bypass this. First, we may have an arbitrary memory read vulnerability somewhere. So far, we haven't seen such a vulnerability, but they exist. Maybe we can read anywhere in the address space, right? Then we can find out what the stack Canary is. Secondly is we can brute force this. We can simply guess the Canary name. Then how many times we need to guess? So in the 32-bit version right now, for GCC, there are 4 bytes, obviously, but the least significant byte is always 0, which means there are only 3 bytes. 3 bytes are 24 bits, okay? So that's 16 million of combinations. 6 million combinations actually is not a huge number. If we keep guessing, it will take several days, it will work. But the problem is, for most of the programs, if you, like the program we just saw, you guess 1, then it will crash the program. Later, the program is created again, it will have a different Canary value. Okay. So, if the Canary value doesn't change, if it takes 1 second to guess once, it will take 194 days. Okay. But actually, it will be much faster than that. So, is there any approach we can guess this faster? Do we really have to guess 60 million times? That's my question. We're going to attack a particular type of function. This type of function will fork itself, and it will keep running. So the fork system call will not generate a new Canary value, which means when you fork itself, it will have the same Canary value. The exe7e will retrieve the new Canary value. A lot of programs we have in the real world, like web servers, they will utilize fork. It has a main process or main thread. When there are new web requests coming in, it may fork itself, create a new thread or new process. In Linux, the difference between thread and process is not very significant. It's a little bit different from your classic OS book. So anyway, yeah, in Linux, everything kind of like a thread. Then when new web requests coming in, the web server will fork itself, then handle those new web requests. So if you crash those new processes, the main ones, the other ones will not be crashed, okay? But they all have the same Canary value, 3 bytes, because the least significant byte is always 0. Okay, so they always have the same 3 bytes, which means we do not have to guess all those 3 bytes at once. So they are not 160 million combinations. You can guess them one by one. Okay, so there are actually only 700 combinations. Go ahead.
Sorry, how do you guess the 1 by 1? Because if you get 2 of the bytes wrong, it's gonna crash it.
But it will not crash the parent. So I show you one example. Let's say this example will much more clear. Okay. So let's say we're going to bypass the Canary from this program. So this is a simplified program, but the idea is similar to those web servers, whatever. This program has a main function. The main function is just a big while loop. It print out. It doesn't really print out anything, just a new line. Then it will fork itself. Okay. After it forks, then it will have the parent process and the child process. So in the child process, it will print out this is the child process and what is the process ID of it. Then it will call the vulnerable function vol, which you are going to exploit. If vol returns successfully, it returns IPT the full. Then it will just exit 0. Okay. The parent will wait for the child process. So at any specific moment, there is only one parent and one child. Okay. There will not be multiple children at one moment. So it will wait for the child process to exit. After the child process exits, it will go back to the beginning of the while loop, which will fork itself again. Okay. Then you will have the parent and child. So the parent will only do this part. We'll just wait for the child, don't do much. The child will call vol. Vol is a little bit more complicated. Vol has a buffer, 40 bytes, but this one will be protected with Canary. So there will be buffer, 40 bytes or more. Then there will be Canary, there will be safety EBP, then there will be return, there will be return address. Then it will, the child will also keep reading from a file. So obviously it can take input from other places like socket from network, like a web server, or in this case, we're just taking input from a file. The file is called temp exploit. So you are going to put something into this file. After it reads this file, it will just do this. If it doesn't find this file, it will keep looking for this file. After it finds the file, it will memory set the global buffer, which is 200 bytes, then read from the file to the global buffer. Then after that, it will print out the child process reads how many bytes from the file, and the guessed calorie is what value. Okay, you're supposed to guess a calorie there. Then it will memory copy from that whatever you read to the local buffer, which is 40 bytes, or maybe a little bit more. Okay. So after that, it will close this program, close this file and remove that file. Okay. So you keep feeding to this child process different values. If your guessed calorie is wrong, what will happen? What? The child process will crash. And how do you know it crashes? It will print out that smashing stack is detected. So what if the calorie you guessed is correct? What will happen?
Keep running,
It will
return to.
So when your guessed calorie is correct, it will not trigger that abort or smashing stack detected. Instead, this function Volfu will successfully return, right? After it successfully return, it will print out IPT the full. Okay. So in this case, if it print out PT the full, it's good. Okay. Then the child process, no, when you guess it wrong, the parent process will create a new child for you to guess again. Okay, make sense? So what we're trying to do is, first I tell you where the buffer is. The buffer is at EBP minus 34, which is 52. Then the calorie is at EBP minus 6, which means the buffer there is 40 bytes. Then we need to overwrite the calorie, and the least significant byte is just 0. Then we're going to overwrite the higher 3 bytes one by one. For each one, we try from 0 to 255. Okay, if it's correct, then we record that number. Then we guess the next number. Make sense?
How do we know if that 1 byte of Canary is correct?
If it's correct, the child program will print out IPT the full.
Won't it only do that if the entire Canary is correct?
No,
How does
because
that work?
because the canary is 4 bytes, right?
Yeah,
The buffer. Then the least significant is 0, 0.
Sure.
So we put 0, 0 there.
right,
We didn't touch the higher 3 bytes.
Yeah.
So it should print out IPT the full because we didn't
Yeah.
change the calorie. Then we guess the first
I
byte.
see,
We
okay.
do not guess the other 2 bytes,
Yeah.
right?
alright,
Yeah. Each time we only
Okay.
override 1 byte.
yeah.
Can you come again? Can you explain that again?
So let me draw this somewhere. So here we have buffer. This is our buffer. Then we have 4 bytes of the calorie, right? So this one actually is always 0. Those 3 we don't know the value. Okay. So we first, so this part we override, this one we can override whatever we want. Here we override 0, 0. Then we override 1 byte here. Only 1 byte. We do not override those 2 bytes. Right? We will try from 0 to 255. So 254 times it will say stash. Only once it will say PD the full. Then we know this one. Then we override this one. Now,
Could you just like, since this is like a brute force thing, could you just add like a second canary to the stack?
add a second canary to
Or
stack.
just like make it longer so it's like, can't.
Yes, but that were, you need to try many more times. Using this approach, you are trying 256 times 3 times. If you want to try those 2 bytes, then they are, how many is that? 2 to the power 16, that's 64K, right?
Yeah, I meant like, as a defense, could you just make the canary longer, like?
Oh, yeah, of course. Yeah, but that were, that's not very effective. That slows down things. For example, for 64-bit version, the canary is 8 bytes, not 4 bytes. Yeah. So this is what we're going to do. Do we still have the, oh, no, we don't have that. We're going to put the share code in our environment variable. Eventually, we want to return to our share code. Before that, we're going to run this piece of program to keep trying. And in the homework, you will write your own program to do this. And my program is only semi-automatic, which means after each byte, I need to move to the next byte. I have to hard code the byte we just guessed. You will see what I mean later. So in the homework, if you, not this week, next week's homework, if you write a fully automated program to do this, you get some bonus points. Actually, it's not that difficult. Basically, you need to read from the output of the program to figure out if you successfully guessed, right? Let's say, which one is this? Bypass. Courage. Okay, where is it? You see, oh yeah, here, see. We have our share code here. Eventually, we still want to return to our share code. Then I'm going to use this script. So this piece of code, as you can see, it will first write 40 bytes, then it will write the different, actually the first one, the least significant is always 0, so we can put a 0 there. So then it will just guess. Computer here. Ooh. It looks like this. Have here because it's Python. So this is while. Should be here. Yeah, this one should be here. This look good?
You need your
Honestly.
four to be indented.
Which one?
Their main.
After the function. After main. I mean, the main function.
Here.
No, on the top, the for loop.
The for loop?
Yeah.
For is been.
Oh, this one. Oh, it's not working. I cannot use tab here. Here I'm using tab. Ooh. What's going on? Well, I copy this. Should work. Yeah, because I copied from slides, that's why. Will this work? It works. Let's try.
That one needs spaces.
Maybe it works. Not outputting anything. So here we don't need to do anything, right? Here I use for. The while should be. This one. This one should be the same as while. This one also should be the same as while. This one should be. On this. Supposed to output something. Oh, it will output to the file, right? Yeah, it will output to the file exploit. It's not actually here. See. I go back to here to see if that file exists. The exploit. Okay, that exists. Looks correct. We have 40 this then 0 0. Why do we have a 0 0 there? Well, put 0 there. So here, if we delete that file, this script should create a new file with a different, say. Oh, 0 0 is correct. So, yeah. Why it's still 0 0? It's good. So the loop has some issue, looks like. Because we wanted it to change to 1, 2, 3, 4, right? I guess. But looks like it's always. Oh, it's changing. Let's see. Oh, it's correct. It is changing. Okay. So, but the first byte, that byte should be just 0, so we don't really need this for it. We need a B here? Anyone familiar with Python? We need to be here?
Yes.
We do. Let me run this again. Here. Remove this. Check. Okay. Remove, okay. Yeah, okay, looks good. Okay, so the script looks good. So now we go back to run the program. Okay, now we are running the program. We already guessed what's done there. Yeah. So we're running the program. So the parent first print out its parent ID, process ID. The child first print out the child process ID. The child read from that exploit file. In that exploit file, we put 42 bytes, which is 40 bytes of garbage, 1 byte of 00, the least significant of the canary. Then we are guessing from 1 there. That's why the guess the canary is 00, last byte, then 1 here. But we're going to restart that. So this one, stacks smashing detected. So now the child process is waiting for the input again. So we go back to our script. And then we start guessing from the beginning, right? So it should keep showing stack smashing detected until we guess the correct byte. When we guess the correct byte, it should do IPT the full, right? And then when that happens, we go here and stop this process. We change our script a little bit, but we don't stop this one. If we stop this one, when we start that process again, it will be a totally new canary value. Now we are at, yeah, we're at here. So this will take a while. We guessed a quarter. No, not yet. Yeah, almost a quarter. Yeah.
It's just going to 255, right?
What?
It's going to 255.
Yes, but this is hex.
Oh.
That's why. Yeah. So 40 is 64 basically.
Is this the case with just fork or with other languages as well, like Go, where it has subroutines?
Yes, so fork is a system call. It doesn't really matter what programming language you use. Yeah, even if you are using Python, eventually it will call the system calls. Yeah. If you guys find, say, IPD the full or the for is there. The last byte should be 00, right? Or the highest byte. Yeah, so let's figure out. Think? No? Or it's just a big number. Pretty. was at the very beginning, we missed it. Oh, no,
Yeah, we got it 500.
it's where is it?
D5.
D5, yeah, it's a big number. Yeah, so then we go back to change our script. So after that, we have D5. Is that syntax correct? I think so. Okay, then we keep guessing. Now we're, yeah, D5 here. More bytes. Our script is a little bit slow because we are using the file to communicate. And so I add a little bit delay there. This can be much faster actually. Big number. D5? D5 was correct, right?
Yeah.
Oh. Yeah, correct.
So you put 1 second in a sleep, right?
Yes, you don't have to.
Is it because of the file IO delays?
Yes, yes, yeah, because the file. We're getting really unlucky here with those huge numbers.
Can we start from the back?
Uh,
The next one.
yeah, but what if it was a small number? It's a little bit weird. Several to go. Oh, are you sure we didn't miss it? Maybe half.
Ah.
Oh my god.
FB is in boy.
Yeah, oh, FB,
B.
wow, that's really unlucky. Yeah, FB here, right? Yeah, okay. Last one. Hopefully this one will be faster. That's not random at all, it's just all big numbers. Yeah. What's there? Halfway? A lot of big lumber. Huh.
Would be like F or something.
Got it? Finally. I see.
C.
Yeah, so. Okay, so after this, what should we have? We don't need this one anymore. We have 40 bytes. Then we have 4 bytes of Canary, which we already got by root forcing. And the Canary is at EBP minus C, right? So we need another 8 bytes of garbage. No, 12 bytes of garbage. 8 bytes to save the EBP, then save the EBP 4 bytes, so total another 12 bytes, right? So do another 12 bytes of garbage. Then after that, we can have the share code address, which we save the somewhere here. ADDA, so AD should be bigger, so we have 1,000 byte of that. So AD we can save it into CD, then DA, FF, FF. Yeah.
Let's read the B in front of it.
What?
We need the B in front of it for bytes.
Oh, yeah. Okay, this should work. So when we run this script, because it's your big while loop, it should keep giving us the flag. So every child process should give us a flag, basically. Yeah, it works. Yeah, so that's how. Yeah.
Why did we have 12 bytes and not 8?
This part, the Canary is at EBP minus 12, right? 12 in decimal.
Yeah.
So that 4 bytes takes forward, which means there will be another 8 bytes from the end of the Canary to the beginning of the saved EBP, right?
Yeah.
Uh,
And then the return.
yes, that's what we mean. So if we have 11 here, it will not work. Yeah, that's way off. Yeah, 11 will not work. So it doesn't crash because, should it crash? Oh, it doesn't crash because,
We guess the canary, right?
no, not because of that. We didn't guess the canary one, right? But when it returns, it still should crash because we overwrite the return.
Return address.
Because there is an exit somewhere.
Yeah.
I think it still crashes. Probably go to STD error. That's why we're not seeing it here. Because, so here, let's see. So Overflow still crashes, right? Yeah, but somehow it's not showing. Yeah. It's not showing segmentation fault, but the Canary is showing it's correct. Yeah. Okay, cool. That's all I have for today. I don't think we need to do this in class. You can do this as homework. Let me show you what homework is like this week. This week the homework is actually quite simple. It's mainly what we did in class, but the save the EBP one may be a little bit tricky. You may need to spend some time to understand that. Then there will be reverse engineering 3 and reverse engineering 4. Not that difficult actually, but there is no source code, pure reverse engineering. Then there is a overflow return 8 and overflow return 8H, which is a hard, difficult version. If you can finish the difficult version, you can get some bonus points. Okay. They're from the same C code, just a little bit different compiler options. Then the battery code is a little bit different, and that's why this version is a little bit more difficult. Start early. If you need any help, just ping me on Slack. Any questions? Good. Okay, then I guess see you guys next week.